So in this clip, we will study the technique in cellular network, which is called sectoring. Sectoring can be a way to reduce the number of co-channel cells, which is usually 6 cells, into something lower by employing directional antennas at the base stations. However, there's a downside to sectoring, which is it's gonna decrease or reduce the trunking efficiencies. So let's look at or review about co-channel interference first. Okay, so let's consider a cellular system with frequency reuse factor of n. Right, so remember n is the number of cells in a cluster. So each cell will be allocated non-overlapping frequency channels. So all these n cells will not interfere with one another. So what could be frequency reuse factor, right? So as we study in the past, it's equal to I square plus I multiplied by j plus j square, where I and j's are integer that is bigger or equal to 0. And we the formula is it's has these expressions because of the assumptions of hexagonal cell. Let's look at example, right? So let's say the transmit bandwidth can provide 35 frequency channels. So there are 35 channels overall for the whole system, and frequency reuse factor is equal to 7. That is, we set I equal to 2 and j is equal to 1. So that means in one cluster there consists of 7 cells, cell 1, 2, 3, 4, 5, 6, 7. And each cell will be assigned 35 divided by 7. So each cell will be providing 5 channels to connect users. So for example, if we're looking at cell number 3, right? So there's a base station at the center. It can connect 5 users at the same time. Okay, all the other cells are doing the same. Okay, but now if you're looking at the whole cellular area, so if this green circle represents a cluster which consists of 7 cells. If we focus on one cell, you see that there's other nearby cluster, right, with the cell that is using the same set of frequency as the one in right here that I draw in the black marker right here. Okay, so let's assume cell radius is equal to r, and d is the distance to the nearest co-channel cell. Okay, so d is this distance, right? So now you see that there's 6 co-channel cells for any given cell. Okay, now as we study earlier, right, we assume that user are at the cell edge. So if we have a user right here, right, the user will receive power from the intended base stations, and the power will be reduced because of the distance. We can approximate the received power, right, of the cell edge user as this. So P0 is the power at the reference distance D0. So it's D0 divided by R raised to power of n, right? So remember n is the path law exponents. So if R or the cell radius is bigger, then the received power will be smaller, right? Because remember, we assume that the user are at the cell edge. Okay, so there are R meter away from the base stations. How about the interference? Okay, so the interference is coming from all the other cell. So for example, if we are looking at the user here, they're also getting the same signal from the same channel from all the other six co-channel cell. Okay, so the interference from a co-channel cell can be approximate as this. Again, it's P0 is the power at the distance D0. So the interference is equal to P0 multiplied with D0 divided by D. So D is the distance to the co-channel cell raised to power of n. Okay? So P0 is approximate transmit power from base station. Let's assume that all the base station has the same transmit power. Now, if we looking at the quality of the signal by looking at the signal to interference power ratio, or SIR, that is the received power. This is the intended of the intended signal divided by the interference, right? You see that I0, right? This is the number of nearest co-channel cell, which currently is equal to 6. It's 6 because you're looking at all the base stations. They are using omnidirectional antenna. So that means it's the antenna that can propagate the signal in every directions. That's why it can interfere in all 6 directions. Okay? So we can simplify, and SIR expressions is equal to this. So 1 over I0 d over r raised to power n. Okay, so if we want to increase SIR, one thing that we can do is we can reduce I0, or reduce the number of nearest co-channel cell. Okay, and that would increase SIR, right? So how do we reduce I0? We can apply the technique which called sectoring, right? So instead of using omnidirectional antennas, right? So here is the antenna at the base stations. So omnidirectional means the antenna that can transmit or radiate signal in all the directions. So it's 360-degree in all directions. So instead of that, we're gonna use something that is more specific or more directional. So we can employ antenna with 100-degree, 120-degree directions coverage. So what it means is, so this antenna will cover only 120-degree in one direction only. So that means if we want to cover all the 360-degree directions, we need 3 sets of this sector antenna. So in a cell, the base station will install 3 sets of directional antenna. The green one, right, will cover only the user in these directions. The orange one will cover the user only in these directions, and the purple one will cover the user only in these directions. And you see that the directions of the signal will be curved by this directional antenna. It's not gonna go in all directions, right? This is a way to limit interference. Now, how does this cut down the number of interference from co-channel cells? So let's imagine, right? We have a cluster right here, and we have a cell in the cluster that we want to take a look, and there's all the other cluster nearby. If we use omnidirectional antenna, then that means there are gonna be 6 co-channel cells. But if we use sectoring with 120-degree directions, then you see that in each base station or each cell, this will be divided into 3 sectors. Okay, so if we are looking at this sector in this directions only, okay, so you see that all the other original co-channel cell, if you're looking at this sectors, then it's going in these directions. Okay, so these are the signal that are using the same frequency and could interfere with one another. So if you look at the cell in the middle, right? So the signal potentially will cover only a third of a cell, but again, right, the signal will not be limited by cell age, right? It could keep going, and it will interfere with the user in these 2 cells. Okay. However, the other 4 cells will not get affected by the signal in this sector. So that means the number of co-channel cell immediately cut down from 6 to only 2. Okay. So you can see here that with 20-degree direction antenna, the I0 is reduced to 2 from original 6. Now, if we use even more narrower antenna, right? For example, 60-degree directional antenna. So that means we have to install 6 sector antenna per cell. The number of co-channel cell will be reduced from 2 to 1. Okay, so that's it's only gonna interfere one co-channel cells. Okay, so the good thing is SIR will be improved, but the bad thing is, as we learn in class, if we divide our resources, which is the number of channels, into different pools. So here in one cell, we're going to divide the number of channels per cell into different sectors. So each sector will get smaller portions of the number of channels. If we are doing this, then we know that because of the trunking principle, the efficiency of using the resource or the channel will be reduced. Okay, so let's take a look at the example, right? So the number of channels for a cell has to be divided into 3 sets in the case that we are using 120-degree sectoring, so that 3 sectors per cell. Let's take a look at the example. Let's say if the number of channel per cell is equal to 24, and if we use 120-degree directional antennas, that means there are 3 sectors per cell. The number of channels per sector will be only 24 divided by 3, which is they're only getting 8 channels. That means in these situations, we have 3 sectors. So this is sector number 1, this is sector number 2, this is sector number 3. Each one has 8 channels. Now, if the user are distributed uniformly, this would mean no problem. For example, if there's only 2 users here in this sector, it can connect to this sector antennas. If there are 2 users here, it's okay too, right? Because the sector has 8 channels, right? And also, if only 2 users here, it's okay too. So it can connect to this sector antennas. But if there are more channels, more user in particular sector, right? Maybe there's some event going on, and people sort of gather in that area. Then you see that with the sector that has only 8 channel, it won't be able to connect everyone. Although the other sectors are free, right? They still have 6 channels left, but they are not able to connect the user in different sectors. Okay, so this is going to be less efficient. Okay, so the result is less trunking. That means they can connect to fewer number of users. Okay. On the other hand, if we use omnidirectional antenna, right? So there's no sectoring. That means the base station can provide the channels to anyone in the cell, right? Doesn't have to be divided into 3 different areas. Then the way we utilize this resource or the channel is more efficiency, right? So there's more trunking, right? And at the end, you get a bigger capacity. So this sectoring technique, as I introduced in the beginning, right? It has plus and minus, right? The plus is we can increase the quality of the signal, which is to increase signal to interference ratio, right? Because we cut down the number of co-channel cells. But on the other hand, the downside is it's going to be less efficient in terms of trunking.